Welcome to Pre-Calculus. Today we will investigate finding distance and bearing. We'll take a look at three examples. Our first example is this word problem in which a boat leaves the harbor entrance and travels 25 miles in the direction north 42 degrees east. The captain then turns the boat 90 degrees and travels another 18 miles in the direction south 48 degrees east. At that time, how far is the boat from the harbor entrance, and what is the bearing of the boat from the harbor entrance? We'll start off by drawing a diagram to represent this boat's travel. So we need to define, first of all, this idea about bearing. Bearing is similar to heading, so we should note the difference here. A heading, which we've seen in previous lessons, is a degree from due north in a clockwise direction. So heading always starts from due north. And a lot of times the way we'll see a heading is just as, for instance, a heading of 25 degrees. So something like that would indicate that we would start at due north and then measure 25 degrees clockwise. And that would tell me the heading of an object, either a person or a vehicle of some kind. So that's different from bearing. Bearing is more flexible. It's not tied to starting simply from due north. And the way bearing starts is it's either from north or south. And from there, we can measure a certain degree either to the east or to the west. So just to see some examples for bearing, if I had something like in this example, north 42 degrees east, well, I'd start with north direction and then head towards the east. So that's to the right or clockwise, something like 42 degrees. We can contrast that with another type of bearing that we have in this problem, south 48 degrees east. And that would start south, and then we would measure 48 degrees to the east. And so you can see that bearing has more flexibility. And you can know that you're dealing with bearing instead of heading, not only by the name bearing, but also by the fact that you'll have two cardinal directions. It'll start north or south, and then a degree measure either to the east or to the west. These both examples had degrees east. So that'll help us draw our diagram. So we'll start here. Let's just find our boat harbor. And we'll just set that here. So initially, the boat is going to travel 25 miles in the direction north 42 degrees east. So to find that direction, I will place due north. And then this is about 45 degrees, a little less than that. So as I start drawing my triangle here, we'll head over about 40, well, exactly 42, almost 45 degrees in the direction of east. Now that's got a magnitude of 25 miles. I do want to mark the distance of that part of the travel. At that moment, once the boat reaches 25 miles in the direction north 42 degrees east, it turns and it makes a 90-degree turn. We are told that it is in the direction of south 48 degrees east. If I add up 48 and 42, that's 90. So we can see that that corner there is a 90 degrees. And it doesn't travel as far. In the first direction, it travels 25 miles. In this second direction, it travels 18 miles. So we'll mark this here 18. And what we're trying to find is this really untraveled distance between the boat after those two directions and the original point of origin, the harbor. And we're trying to do two things. We're trying to find the bearing of it. We're also trying to find how far is it. So the diagram helps quite a bit. I see I have a triangle, and I need to investigate about how can I find these missing pieces in order to find both the length of this green direction and also the bearing from the harbor entrance. So again, we would say from the harbor entrance, what's the bearing? So the first thing I notice is we're in a right triangle. So what I'll do is I'm going to label these vertices just so I can see where A, B, and C are relative to one another. So I'll just start with the harbor. That can be vertex A. The boat out here has to be vertex B because vertex C is reserved for the 90. So then in terms of side length measures, if angle A is the harbor, this distance 18 miles is my side A. It's opposite that vertex. And then 25 miles is opposite B. So that's my side B. So what we're looking for is side C. And then we're also looking for this lower angle as well. Well, if I'm in a right triangle and I'm looking for, in this case, the hypotenuse, I can use Pythagorean theorem. A squared plus B squared equals C squared. And I see that because of the 90. It's really because of the 90 degrees. So I'm just going to start filling in from my marked dimensions. A, I had assigned the length of 18. B has the length of 25. And that is going to allow us to solve for C. That equals C squared. So I do have to take the square root of both sides in order to get just C. But let's go ahead and calculate the square root of 18 squared plus 25 squared. So we'll take it to the calculator. Once I've got that set up, I want to use the calculator to evaluate. So square root of 18 squared plus 25 squared. And that's going to give us, if I round to the nearest tenth, a length of 30.8 miles. 30.8 miles. And that solves our first question. That's the distance from the boat back to the harbor. I'll go ahead and box that, 30.8 miles. Our second question has to do with an angle measure. We're trying to find what is the bearing of the boat from the harbor entrance. So for this setup, I'm looking for the measure of angle A. Now, I don't have a lot of information about the angles other than I have a 90 here in the corner at C. So to find the missing angle A there, what I want to do is set up a trigonometric ratio. And I just need to investigate the pieces that I've got. At this point, I have all side lengths, but I'd like to use the two that I was given originally, so it's not an estimate, it's an exact value. So from angle A, side A is opposite. And then from angle A, side B is adjacent. So I'm looking for the trig ratio that is opposite over adjacent. And we don't have to look far. That trig ratio is going to be tangent. That's defined as opposite over adjacent. So we'll set up our equation to solve for our angle measure at A. So I'll put tangent of A. Then I'm actually going to put in the values here. The length of the opposite side is 18. Length of adjacent side, 25. And that's ready for me to solve. So recall, if I have tangent of an angle, but I want the angle measure, I can apply the inverse tangent ratio. And what that will do is it'll cancel the tangent function. They're inverses of each other, and it'll just leave me with angle A. And that's going to be equal to the inverse tangent of 18 over 25. So like with our first task there, we're going to take this to the calculator to finalize the calculation. So here on Desmos, to find inverse tangent, you go to the keypad and select the functions tab in the trig option, and that'll give you inverse tangent. So I'll make sure to plug it in there to a new field. And then we've got our quotient here, 18 over 25. Now I do need to be sure that I'm in degrees. So recall on Desmos to find the setting to toggle between radians and degrees is this graph options, graph settings. Radians and degrees are at the lower side of that menu. I'm just going to click degrees so that it's highlighted. And that's giving me this measure 35.8 degrees, 35.8 degrees. So that's the measure of angle A is going to be 35.8 degrees. But that's not really our answer. Remember, that's angle A. We want to know what's the bearing of the boat from the harbor entrance. Well, if I'm going to calculate the bearing of the boat from the harbor entrance, I need to include not only my 35.8 degrees angle A, but also the 42 degrees. I need all the way back to due north. So the bearing of the boat from the harbor is going to be the sum of 35.8 plus the original bearing of the boat, 42 degrees. And that's going to give me a total of 77, if I add that together, 0.8 degrees. And I need to really mark that in this bearing format. So I had started off from due north. So that's how I'm going to begin my bearing here. It's going to be north 77.8 degrees east. And we'll box our bearing there. That completes our two tasks for this question. We were looking for the distance of the boat from the harbor and also the bearing of the boat from the harbor entrance. Our second example is this one about 3 towns in California. We know, first of all, that Lompoc, California is 18 miles due south of Nipomo. I want to place those two cities in a diagram with relation to one another. So they're north and south, so they're vertically aligned to each other. And Lompoc is south from Nipomo. And we know specifically it's 18 miles from Nipomo to Lompoc. So we'll measure, or we'll mark that 18 miles. A third town, Bealton, California, is due east of Lompoc and south 65 degrees east from Nipomo. Our task here is to find out how far is Lompoc from Bealton. So let's place this third town. We know that it's due east from Lompoc. So I don't know how far it is from Lompoc. What I do know, however, is that it's a bearing of south 65 degrees east from Nipomo. So if I place south, that's directly in the downward direction, and then mark 65 degrees, I can place roughly this third town, Bealton. And we'll go ahead and mark the angle there as well. The angle here that we found. So if that's south 65 degrees east, this is in fact 65 degrees. Again, east is in the right direction. So that's our setup. That's our triangle. And what we're trying to find is the distance from Lompoc to Bealton. I'll mark it there as X. So the arrangement's similar to what we saw in our first example. Definitely, this is a right triangle. The 90 degrees there at the kind of the interchange from Nipomo to Lompoc, Lompoc to Bealton. I want to find that missing side of the triangle, the missing leg. Now, one piece of information I have at the outset in this question is one of the angles in the triangle. I actually know that this upper angle at Nipomo is 65 degrees. So just thinking about how we could find a missing side, if I know an angle and one other side, I could set up a trigonometric ratio similar to how we set up in the previous problem when we were looking for heading. So I see that if I'm at 65 degrees, the side opposite is our x and the side adjacent is 18. So we're looking again at tangent of theta, since that is opposite side divided by adjacent. So we're going to set up for this question. It's going to be the tangent of 65 degrees equals x, which is opposite from 65 degrees, over 18, which is adjacent. And that equation we can easily solve just by multiplying both sides by 18. And our distance there is going to be given by this expression, 18 times tangent of 65 degrees. So we'll take that to the calculator and finalize that calculation. So we'll type in 18 times tangent of 65 degrees. And right away we get our solution. That is 38.6 miles. .6 miles. And that solves that example. So only one question that we're trying to solve for here. Notice that our strategy was similar in terms of the setup. What was different here was the information we had provided. I had one angle here and one side, whereas in the previous question, I just had two side lengths. Our last question is one that involves two observation points looking out on a ship. So a ship's anchored off a long straight shoreline that runs north and south. So what I'm going to do is I'm going to start to create a diagram. Here's a north-south shoreline. We'll position north and south so we can see it. From two observation points 18 miles apart on shore, the bearings of the ship are north 31 degrees east. So let's place one of these observation points. And we'll just start with this lower one. Let's call that observation A. So the ship is on a bearing of north 31 degrees east from this one. So north is the upward direction and east is to the right. And so I'm going to give about 31 degrees there as my bearing from this observation today out to the ship. So we'll complete that line in a moment. Let's find this second observation point. So it's north of observation A is here observation B. I do know that the distance between those guys, if I were to mark that, is 18 miles. So let's just highlight that distance on the shore between the two observation points is 18 miles. And then the ship from observation B has a different bearing. It's south 53 degrees east. So south and then more steeply 53 degrees. So we'll mark that angle there. And what that gives us is this triangle with out here at point C, that's the ship. We just make a rough drawing, that's the ship. What we're trying to discover is what's the distance from the ship to each of the observation points. So just in terms of my triangle, if I label according to my vertices, so I don't know if it's a right triangle or not, but I put the measure of angle C here as the largest angle. So the side opposite at 18 miles in length is going to be side C. If observation point A is down here, the side opposite it is going to be side A. So we are looking for side A. And also opposite from observation point B is side B. We're looking for side B. So according to my arrangement, I don't know if it's a right triangle. That's different from my first two examples. What I do see though is I have angles and a side. Now, I can find this third angle at C using the triangle angle sum theorem. So I'm going to do that really quickly. I'm just going to take 180 and subtract 53 and 31. So recall all three angles should add up to 180. So that kind of confirms what we were thinking about this angle. It's not 90 degrees, it's bigger than 90, it's 96 degrees. Now, if I want to find two side lengths that are missing, and I have one of the side lengths in three angle measures, I can use the law of sines. So remember what law of sines says. It says that if I've got a ratio, sine of angle A divided by the length of side A, it will equal sine of angle B divided by side B, which in turn will equal sine of angle C over side C. So I want to choose one of these first that has both parts, both the angle and the side. And what I see is that I've got now side C, 18 miles, angle C, 96. So I want to start with sine of C over C. And what we'll do is we'll solve separately for A and B. So let's set up our equations. Our first equation is going to be sine of, so we'll start with our C, 96 degrees over 18 miles. That's the one that we can complete, is going to equal, let's solve for A, sine of A, which is 31 degrees over side A. Remember, to solve an equation like this that's a proportion set up by the law of sines, we cross multiply. So it's going to be A times sine of 96 degrees equals 18 times sine of 31 degrees. And then to finalize solution there, I would just divide by sine of 96 degrees. And that'll isolate for us A here on the left and gives us a ratio here to calculate that side A. So we'll do that just now. Let's take this over to our calculator. So again, that setup was a fraction, and it's going to be 18 times sine of 31 degrees over sine of 96 degrees. And that's giving us a distance, if I round to the nearest tenth, of 9.3 miles for side A. So 9.3 miles. And we can mark that here on our diagram, 9.31 miles. We'll go with 9.3. So all that's left for us to solve for now is the length of side B. So I'm going back to the law of sines, and I'm going to pick up, again, sine of C over C. That's the one that's complete, and it's not approximated. I could use sine A over A now, but that 9.3, we rounded it. Whereas sine of 96 degrees over 18 miles is exact. So again, we're going to set this up for side B now. So it's sine of angle B, 53 degrees, over the length of side B. Once I got that set up, it's again cross multiplying. So that gives me B times sine of 96 degrees equals 18 times sine of 53 degrees. And just as in our first calculation to solve here, I'm going to divide by the sine of 96 degrees. That'll cancel here on the left. And that we can now solve for side B. So a very similar setup. It's just my angle of 31 degrees has changed to 53 degrees. So in fact, what we could do is just use the same setup that we had just typed in and just substitute out 53 degrees for 31 degrees. And that's going to give me a length of 14.5 miles, 14.5 miles. And that concludes this third example where we are looking for two side lengths in a triangle that's not a right triangle, but we can do it anyhow using the law of sines. Thanks for joining for this investigation of bearing and heading. See you soon.